So here we are in the topic of machine learning again. In the previous class, we talked about recursive neural networks. Today, we will see three topics: distributional semantics, topics, and topic detection, and automatic summarization. So distributional semantics is based on the idea that the semantics of some word can be inferred from the surrounding words. So this may seem a bit strange, but you can make a test. You can remove one word from a sentence and ask people to complete it. In many cases, they will find the same word or some similar word. Of course, all depends on the context, so maybe it's a very general context and so on. But if you can infer a missing word from the remaining words, this means that the semantics of a word depends somehow on the semantics of its surroundings. And the statistical approach to this is to build a language model. So what we call a language model is a probability distribution over sequences. So you notice that here I don't put commas. It's because it's not the probability of variables, it's the probability of one sequence of words in a given order. So of course, this probability will be very small because having given words in a given order may occur only once in a corpus. So it will be very small and difficult to deal with. And this is why we simplify, we approximate by taking n-grams. So an n-gram is a group of n words in the right order. And in this case, what we calculate is the conditional probability of a word depending on the n-1 preceding words, with the special case of unigrams where you have only one word. Now, what happens here is that we often have zero probability, especially when our corpus is small. So some words may be missing or some word combinations may be missing. To avoid zero probability, we use smoothing. So this is a special kind of smoothing which has been implemented in Python. So I would like to give you the main idea. So it works for all kind of n-grams. And here I'm illustrating it with b-grams so that you can capture the idea. This is a b-gram. So word I conditionally to word I-1. And what we take here is a sum of two things. The second one is the corresponding unigram. We calibrate between the two terms, first term, second term, with a constant lambda, well, it's not, it's a constant for wi, but it does depend on wi minus 1. And we calculate these by advancing in the sentence. Now, what is the first term? In the first term, we count all pairs wi minus 1 wi in the corpus divided by all pairs where wi minus 1 is the first word. So this is among all pairs wi minus 1 something. How many times is something equal to wi? And we take the maximum between this and 0. Okay, this is a bit strange because this is counting, so it's always positive. Yes, but we subtract a delta from this. Why do we subtract a delta? Because if we don't, then maybe we will get 1 here. And if we get 1 here, then this part is useless. So we want this to be smaller than the exact count so that we keep some room for the unigram. And our delta will be the same always. It can be less than 1 or not. And if it's bigger than 1 and we get something negative here, then we just take 0. How do we count the probability of this unigram? So it's not an arbitrary probability. It's, again, the Kneese-Ney probability, which is find me all the cases of words which precede wi and that occur in the corpus. So all the pairs that occur in the corpus divided by the probability of all pairs of the corpus. Okay. And this is what we call the unigram probability. Now, these lambda terms are calculated as usual in smoothing in such a way that this here respects the axioms of conditional probability. So the fact that it has to be equal to 1 for all wi. Okay, and there is a Python package for this, KNLM, and this allows you to avoid zero probability. Now, one important concept when we are dealing with language models in deep learning is the concept of embedding. The idea is that your vocabulary can be quite big, especially if you don't lemmatize at all. You just take the words as they are in all possible forms, so all forms of conjugated verbs, of declined nouns, and so on. Your vocabulary can easily be in the many tens of thousands of words. And if you want to do calculations with these vectors, if you take a vector of the size of your vocabulary, then you are in a very high dimensional space. So to reduce dimensionality, we can use approaches to pack all of this information into a smaller number of dimensions. And we take, for example, 300. So 300 is not simple Euclidean space like the one of Euclidean geometry, which we taught in school. It's much bigger, but it's still a reasonable size to do calculations. So it's a compromise between having the whole of the vocabulary, many tens of thousands, and having something really small on the plane or in a three-dimensional space. Now, we are packing the vectors, so the vocabulary vectors are all projected into this space, but this projection is not linear. It's done in such a way that, first of all, Euclidean distance in this space is correlated with semantic distance. And I'm very careful in using the word correlated because it means that statistically, words that are semantically close are also geometrically close in this space, but this is purely statistical. And furthermore, some linguistic transformations are correlated to directions in the Euclidean space. So, for example, take the plural. If you notice that you have a vector for man, woman, and a vector for women, the plural, then you can calculate the difference of these two vectors, and this is the displacement vector, the translation vector from woman to woman. If your embedding is of good quality, is rich, then going from table to tables, plural, will be a vector in a direction more or less parallel to the one going from woman to woman, from cat to cats, and so on. So taking the plural is a vector, statistically speaking, again, in this embedded space, and changing gender is another vector, and taking the superlative big, bigger, biggest is again a vector, and so on. Now, of course, this is only more or less true, but it has been observed. So it's not imagination, it does occur, but it is statistical. We have many approaches. I will describe the two most popular approaches for embeddings defined in 2013 by Mikolov. The first one is called continuous bag of words. So it's a kind of bag of words, and it's continuous because we are in the space of real numbers. It's a neural network that looks like this. On the left, you have the input layer, where you have one hot vector. So a one hot vector is a vector which has only one unit dimension and the rest is 0. These vectors have the size of the vocabulary, so they can be easily vectors of dimension 10,000, and they are unitary. So each of these vectors represents one word in the vocabulary. Here we are taking C of them. C is called the size of the window. The idea is to say, in my text, I take a sliding window of size C+1, and the word I'm interested in will be in the middle, and I have C divided by 2 on one side, C divided by 2 on the other side, and these are the C words of the context of the word I'm interested in. Now, on the other side of the network, on the output side, I will use the one hot vector of the omitted word. So in my context of C+1 words, I omit the one in the middle, and I'm using that one on the other side of the network for training. Now, what happens inside the network? First, I take the average of these vectors. And the average is very easy to calculate. It's just a vector of the same dimensionality as there. And with ones for all of these, and divided by C. And then I have here this matrix W for going from these vectors and actually from the average of these vectors into a hidden layer. And this matrix I'm going to train. This hidden layer has the size of the embedding. It's the size is, for example, 300, as we said. So here we have vectors of size 10,000. We take an average, and then we arrive into a vector of size 300. So this is the first matrix to learn. And then from this, we go again to a vector of the size of the vocabulary. This layer here will have numbers that can be big. And here we have a softmax function between those two layers of the same size, so that here we get a probability vector. So here it's again of the size of the vocabulary, tens of thousands, but the sum of all values is equal to 1. Intuitively, what we get is that here we obtain the probability of each word in the vocabulary of being in the context of this one word, which is the one we have omitted. Now, how do I know which one is this word? During training, I will have here for training the one hot vector of this word, and I will try to approach with this softmax the one hot vector. So my training will consist in finding matrices W and W prime such that from a given context, I get the best possible prediction of this word, which I use for training. Now, of course, what may happen is that I have exactly the same context for two different words. Then I will have probabilities here, both for this word and for some other word. This will be my training. And what will be the prediction? Well, the prediction will be I input a context, a window, and in the output, I take the argmax, and this will be the most probable word to be in the middle of the context. So if I want to write this mathematically, as you see, first I take the average of all one hot vectors of the context, and then I multiply by this first matrix, W, to obtain the hidden layer, H. Then I multiply the hidden layer by this second matrix, W prime, to get the almost output layer. And then I apply softmax to this There should be a bold U, to obtain the real output layer. So mathematically, this network is quite simple. It's the softmax of W prime multiplied by W multiplied by bar. The bar means average. Okay, and now you see why it is called back of words, because by putting them all together and taking the average of the vectors, we lose completely the order of words. Okay, if there was no average operation, we could still say that the fact that this one is the first may influence the matrix, and then giving the same words in a different order would maybe produce a different result. No, it's not possible here because we first take the average. So the order disappears. Okay, and so what we model is a C-gram, so an n-gram with n equals to capital C, which is the sliding window, with the convention that when we write this, we don't mean the C preceding words, we mean half and half, so half preceding and half succeeding words. The loss formula, and here I'm just taking the formula from a previous slide, is simply a term on the word which on the only coordinate of the word with which we train our network, plus the log of the sum of exponentials of probabilities of others. So we want to keep this small in order to have a small loss. And then once again, like in previous slides, to train my network, I will derive the loss, deriving the loss upon the second matrix and the first matrix. I get again the formulas, and I can write this as a tensor of two matrices, and same thing for the other one. And you see here it's symmetric. So the derivation of the loss with respect to W prime is involving W, and the one of W is involving W prime. And in both cases, you have the average of X. So the gradient descent will use these two calculations, which are quite symmetric and quite easy to calculate. So training is easy. We just take all windows, C+1, we remove one term, place the remaining ones in the input, the one we have removed in the output, and we start propagation, back propagation, and so on. Here is the code in Python using Keras. In Keras, you have an embedding level, a layer special for embeddings. Here I give an example with a file which you can download from the Gutenberg project. It's the text of Alice in Wonderland. I break this file into lines and not even into sentences, simply into lines. And then I tokenize it. And it looks like this. This tokenizer class will do two things. It will break the text into words. It will put these words in a dictionary indexed by integer numbers, and it will replace the words by their indices and will return an array of arrays of numbers, which are the indexes of the words. If we optimize this, then small indices will be the most frequent words. Unoptimized small indices will be the first word that appeared in the corpus. And here we are generating our data. So we are building contexts and labels. So the contexts will be the windows on the left, on the right, and labels will be the words in the middle, which we will use as trainers for categorical probability. And this yield is for generate data to provide us with context, so a pair context and word in the middle of the context for as many as possible in the corpus. So this is with this loop, with these two loops for and here the yield, I can use this function as an iterator. And here are examples of context. So you see here, the first, there is no left part because it's the first, it's the beginning of the text. So I have removed the 96 and I have 34, 28 are the two words following. I'm using a sliding window of size 4. And then 96, 34, 16, 5. There's something wrong with these data. I will have to look at it. But the idea is that at the beginning, you take only one part of the sliding window, then you add more, and then starting from the third word, you have a complete sliding window, and what is missing is the 28 in the middle, and then you put the 28 and you extract the 16 and so on. So these contexts are correct, but the X's here are not compatible. And the label Y will be the one hot vector where you have a 1 at position 96, at position 34, 28, and so on. In Keras, you start a sequential neural network and then you add layers. The first layer will be an embedding layer. The input length will be twice the window size. So here, instead of giving C, we give C divided by 2, so that we need to multiply afterwards. Input dim is the size of the vocabulary. So each vector has the size of the vocabulary, and output dim is the size of the embedding. Then we add this, the mean of the x's, and then we add a dense layer for the softmax activation. We compile it and we use it. And here what I'm doing is I'm I'm writing the weights of words. Okay. So this is an example of code. What you should keep in mind is the fact that you start with a context and you train the model to obtain the word in the middle of the context. Now, the other kind of embedding introduced by the same authors in the same article, so they are a bit complementary, does it the other way around. We start with one word, so this is one hot vector, and in the output, we obtain the context. So C vectors. The difference here is that there is no averaging. So here, this context has a given order. Otherwise, in the middle, we have exactly the same thing, an embedding size layer, and here we have a softmax. Now, this means that intuitively, we input a single word, and in the output, we get the various probability distributions of windows having this word in the middle. And of course, we can take an argmax to obtain the context, which is the most probable. If you look at the math, then once again, you get this kind of formula, again involving the two matrices, W and W prime, without the average. I don't know why I put this. It's a wrong, this is wrong. There is no average. After all, it's just a single vector, X. And similarly here for gradient descent, we have this kind of expressions. And again, derivation by W gives us something involving W prime, and derivation by W prime gives us something involving W. Why is it called a skip gram? Because we take an n-gram and we skip one word, the one which is in the middle. Now, both with bow, CBOW, continuous backwards, and with skip grams, there is a technique that improves the result and also the calculation time, which is called negative sampling. So negative sampling consists in doing two things at the same time. One is training your model on words that are candidates for being in the context of a given word, and at the same time, taking words which are definitely not in that context and putting them to zero. So training the network to output zero for them. So this means we are moving in two directions. We are moving in a positive direction while putting interesting and pertinent weights for words which are in the context. And at the same time, we put zeros. So we want our results to converge with zero for words that are definitely out of context. How many? This is a hyperparameter. Usually it's around 20 at the same time, and this is called negative sampling. Now, besides these two cases, there is a technique called glove. Glove is not a neural network. It's a technique for obtaining an embedding, which then is used in neural networks. So you have seen it in neural networks, but to obtain this embedding, you don't need a neural network. Okay, and GLOVE is an invention again by Manning in Stanford, and they have created some very nice embeddings. So sometimes when we say GLOVE, we mean the technique. Sometimes we mean the embeddings that you can download freely from the site. Now, what is the idea of GLOVE? So they say that if I want to compare semantically two words, taking conditional probabilities is not always very adequate. So for example, here I'm taking word solid, gas, water, fashion. So you see fashion is out of context. I'm comparing solid with ice, gas with ice, water with ice, fashion with ice. I'm taking the conditional probability of solid being in the same context, so close to, in the same window as ice. And you see that solid, this probability is a bit higher than that one, but the difference is very small and both values are very small. So compare them in an absolute way is not very pertinent. Furthermore, you see that fashion is just a bit smaller than gas, and fashion is semantically much farther away from ice than gas. Same thing with steam. Their idea is to take the ratio of conditional probabilities. So if I want to compare similarity of ice and steam, I can take the ratio for different case. And if I take here the word solid and the word water, you see that with solid I get a high value, 8. This means that probability of having solid ice is much higher than probability of having solid steam. If I take water and fashion, I have something around 1. If I take gas, I have something quite small. Now, starting with this remark, the idea is to use other words, which we call WK tilde, and the tilde means that these are arbitrary words we will use to compare the similarity of WI and WJ. And starting with this observation, we say there should be a ratio of conditional probabilities between I and K and J and K. Okay? Now, what will we use as function f? And the first intuition is to say we want an embedding which is a vector space. In a vector space, it's nice to have linear applications. For example, subtracting vectors. This is linear, so it's quite natural in a vector space. So let's take as f not simply a function of wi, wj, but a function of the difference between wi and wj. Okay? Now, this function, we want it to be linear to make things simpler and to make things more natural in a vector space. Why not taking here a product of vectors? Because on the right side, you have a scalar. Here you have a vector, and here you have a vector. So to get from two vectors to a scalar, the easiest way is to take the scalar product. Okay? Now, these probabilities can be obtained by counting, but I can also consider that they are obtained by multiplying vectors. And this is symmetric for both sides and quite natural. So all of this sounds nice, but what is F? Well, here you have this F of this scalar, and here you have the ratio of F of two other scalar products. This makes, this is an equation for F, and the solution is to take an exponential. Exponential saying that this will be the log of that one minus the log of that one. And now I'm missing some things. I'm missing a constant on the left. And if I put a constant on the left for I, and I want this to be symmetric, I can put also, I can add a constant for K, and now I get a symmetric formula. Now in these two slides, I followed the article by Manning and Pennington, and it's not a mathematical proof of any kind, it's just intuition. So how do we change our formula according to our intuition to get something that has chances to work? Now, here, this is very nice, but what happens when our xik tends to 0? Our log will tend to minus infinity. To avoid this, we will use a function which will converge to 0 faster than log, than square log. So here we get something positive because of the square. And by multiplying it by this function, we can avoid divergence. Now, what will this function be? What they propose is this here. So the ratio between x and the maximum value of x, so that this ratio is always smaller than 1, at the power alpha, where alpha is empirically chosen as being 3/4. Okay, and this gives us a formula for calculating vectors and obtaining this embedding. So you see, it's not at all a neural network. It's just calculations of counts in, depending on the presence of words in a sliding window. And as it seems in this paper, we're taking a corpus like Wikipedia and GigaWord, you get results that are better than SIBO and SkipCard. So these two diagrams are from this initial paper by Pennington and Manning. You have to understand what is written here. The y-axis in both cases is accuracy. And here you have training time, which is proportional to iterations in GloVe. So iterations mean doing the calculations again and again and obtaining the best parameters. And for SIBO and skipgram, it's proportional to the number of negative samples. So how many negative samples do I use? And you see that here for 10 negative samples, I get the best value, but then it decreases. And for glove, I get a much better accuracy, no matter how many negative samples I use. Okay, so now you know that you have different choices for embeddings. You can always take the glove up embedding as it is and use it in your neural networks. This means that you take an arbitrary text in the same language and you vectorize it. So every word becomes a point in this vector space of the embedding. This is the average use of embeddings, but you also know how to create an embedding if your corpus has something special, if it's a corpus in a given domain. So if all of your texts deal with a specific domain, then you should better create your own embedding using one of these methods. So you create the embedding and you evaluate it. And the evaluation can be either how good is it in a given task, or if you want to use this property of having directions in your embedding for specific linguistic transformations, then you can evaluate this. You can say, I take 100 words with two genders, so either adjectives that are different or nouns that are different, king, queen, and so on, man, woman, and I compare the geometric directions going from male to female. What is my precision? What is my recall? And you can do this once you have finished your embedding, or you can do this during the preparation of your embedding, so an evaluation, so that you stop when you have achieved a given threshold. Okay, so this is what I wanted to tell you about embeddings. What you should keep in mind is what is an embedding? When do I use the existing embeddings? When do I create my own embedding? And if I create my own embedding, how do I evaluate it? And now let's switch to a different subject called topic modeling. So it's different, but as we will see, there is a connection between the two. The idea of topic modeling is that we make the hypothesis that in our documents we have topics. And topics are subjects, themes. Now these topics are represented by words, but not in a unique way. So the same word can be part of the representation of more than one topics. So not only a word can have different meanings, but even with the same meaning, the word can appear in more than one topics. So in fact, we have a probability distribution of words belonging to topics and another probability distribution of topics appearing in documents. What are topics useful for? For example, for classifying documents. if you want to classify text as belonging to sports or news or religion or science, then you can explore them, find topics, and consider that this topic is entirely a topic of religion or a topic of sports, and this topic is more or less is more connected to this domain than to the other one, and so on. Also, topics can be used for detecting illegal content, because often hatred and racism are not explicit, do not use explicit words, but a combination of words, and these combination of words could be interpreted as topics. Now, the first method we will see to detect and obtain topics is LSA. We take our documents and here we are. So LSA is latent semantic analysis. So it's latent because it's an unsupervised classification of topics. We don't know in advance what the topics will be. We obtain topics as groups of words, but we still have, as humans, we have to read these words to find out whether they are connected to some theme or whether they are just collections of words with no apparent connection. So it's an area which is quite open and ambiguous, and this is expressed by the L as latent. Now, we take a matrix of documents and terms. I'm talking about terms, so I consider that you have done terminological analysis. It's not words anymore, but terms. And in this matrix, my rows will be documents and my columns will be terms. So once again, it's a bag of terms. Order has disappeared. I'm just counting the presence of these terms in the documents. Since presence means counting, and counting depends on many things, depends on the size of the corpus and so on, I will use a measure which is very fundamental, and I should have introduced this notion much earlier in this class. Today is the last lecture, and this measure should have been given already in the first lecture. It's very fundamental. It's called TF-IDF. TF-IDF is term frequency multiplied by inverse document frequency, or term frequency divided by document frequency. This means that the TF-IDF of a term in a given document, so it's a given term in a given document, is the frequency of the term in the document, so the count of the term in the document, divided by the number of documents in which the term occurs. And here we are counting documents and not occurrences of terms. The idea is that if you take a very common word, a grammatical word like the, this word will appear in all, maybe all documents of your corpus. So your denominator will be high. In each document, it will appear a few times, but with a very high denominator, TF-IDF will be very small. A word which is infrequent and appears only in one document, the TF-IDF will be the count of the word in the document divided by 1. So it will be high because this word is characteristic of the document. Now, taken as a value per se, TF-IDF has no meaning. And therefore, we use also a logarithm to make things a bit smoother. But it can be useful when comparing TF-IDFs of words. And in particular, what we often do is for a given corpus, we attach to each document the highest TF-IDF values of words. This means we get for each document the words that are characteristic of this document. Okay, so now in our matrix, we have documents in rows and terms in columns. And inside the cells, we have TF-IDF values. Now, this is a very big matrix. It has on one side the size of the vocabulary, on the other side the size of the corpus. To reduce this, we use singular value decomposition. Here the idea is that we take an arbitrary matrix of real numbers and we do calculations to obtain its decomposition as a product of 3 matrices. The first and the last are orthogonal matrices, this doesn't matter. And the one of the middle is a diagonal matrix. It has only positive values, and we can do these calculations in such a way that these values on the diagonal are in decreasing order. Okay, they are positive, they are real, so you can compare them, you have a total order, you can put them in decreasing order. Now, once you have done this, you can take a submatrix. You can take a square matrix of much smaller size. In the middle, the corresponding matrices on both sides, and you will get a new matrix, which is not the same as the one you started with, but which is as close as possible to it in a lower dimension. So it's a typical case of dimensionality reduction with a minimum of loss of information. So now we have columns that are topics, and in fact, they are aggregated terms that we don't know how they have been aggregated, and rows which are aggregated documents. Now, the size of this reduced matrix will give us the number of topics. We have to decide the number of topics. And once we have decided, we can do the calculations and we obtain our topics as aggregations of words. The first matrix, the one on the left, will give us the aggregation going from all documents to the reduced number. The one on the right will be the aggregation of all terms to the reduced, to the aggregated version. And but for this calculation to take place, we need the number of topics. How do we choose the number of topics? Now, for this, we have several techniques. The one I will describe is called coherence. Coherence is something measured on each topic separately. So it's not a comparison between topics. It's for each topic, we calculate its coherence. And since we want to do things internally, we have formulas using the probability of words being in the same context and doing this for a large amount of words. So we take, no, not a large amount. This is, these are the words of the topic, and we are calculating all possibilities of pairs in this topic, probability of being in the same context, divided by probability of each one of the words in the corpus. We take the log of this and then sums, and we divide by this. And same thing here, only this one is symmetric, and this one is asymmetric since we divide by the probability of the second one only. Once again, these values in an absolute manner have no importance. They become important when we compare them for a different number of topics. So in this diagram, you have here the values of coherence for UCI, sorry. And for each value of topics, we have done the calculation and calculated the coherence of each topic, and then we took the average, the arithmetic mean of these values for each topic. And you see that we have a local maximum here and a more global maximum here. So 32, for 32 topics, we get the best coherence value. And then, of course, we can continue. This means a lot of calculations, but once you got the topics, they can be very useful in your corpus. Here you have positive value, but very often you get negative values since it's the log of something that has many chances of being smaller than 1. Here you see this is the probability of, this is a joint probability divided by a margin. So if this epsilon is small enough, then this here will always be smaller than that. So this log will always be negative. So you don't be surprised if you get negative values. As I said, the values per se have no importance. What is important is comparing them. Here's the code for latent semantic analysis. Once again, we use a vectorizer, but this time we ask it to be TF-IDF. We clean, this is for cleaning the text, going through the wordlet lemmatizer. So this is the clean, I think I've placed this on Moodle. And here it's, we have cleaned it up. And then we vectorize it by removing stop words and asking to have a maximum 1000 features. And here is singular vector decomposition, which is the LSA model. So LSA is simply this linear algebra operation of singular value decomposition. We apply this model to our text as it has been vectorized, and here we get the most important words for each topic. Now, these are not important for the machine, they are important for us humans to evaluate the quality of our topics, because coherence is what we call an intrinsic method. Intrinsic means that it's a numeric value that we obtain solely by our calculations, without any other resource. But you can also evaluate topics in an extrinsic manner. So, for example, you can take a semantic similarity method, for example, distance in an embedding, and you can compare the semantic similarity of words in a topic. Now, is this a correct approach? It can be useful if your semantic similarity measure is appropriate. But then again, it depends on the nature of your measure. So the typical example is taking WordNet and taking distance in WordNet as the inverse of a similarity measure. This works fine when you have terms hierarchically related. For example, the distance between a cat and a feline is very small. Distance between a cat and a dog is a bit bigger, since we have to move from cats to felines to mammals, and then from mammals to canines and dogs. But still we are in the domain of animals, so this distance is still small. And this allows us to get semantic similarity, but it's a special kind of semantic similarity based on hierarchy. If I want to compare a car and fuel, then in WordNet, I will get a very large distance, because a car is a vehicle, which is an artifact, and fuel is a chemical substance, which is a fluid, and going from cars to vehicles to artifacts to material entities and going down in fluids and fuel, well, it's a very long path. So the distance between cars and fuel is very long. But when we want to evaluate semantic coherence, if we have car and fuel in the same topic, this is perfectly natural. Because when we talk about cars, often we talk about fuel, like in fuel consumption, fuel consummation. So all depends on the nature of your semantic similarity measure. And then again, if all computer methods fail, you can always ask for a human jury. So one way of evaluating the quality of your topics is to show them to a group of people using the same protocol and ask them which ones they consider the most pertinent. Then take the marks by all of these people and out of them obtain an average. So this is also a perfectly appropriate method for evaluating pertinence of topics. And here you can evaluate by yourself. I took a topic of Australian newspaper titles, not even articles, just titles. It's a corpus of very small documents. I asked for 10 topics. I used LSA. And so here you can see that some words appear very often. Australia, Australian, Australia, Australia. Here in this topic, you have many proper names. So as humans, we can call this, we can give this topic a nickname. We can call it the topic of proper names. Then this one has death and crash and fire. So this is rather a topic of disasters. This one has court, charge, accused, murder. So this is rather a criminal topic. But then again, you find death like here also, fire like here also. So you see this is more disaster oriented, and this is more criminal charge oriented. And then there are some of them where you can't really find a common theme of words, like here, council, fire, rise, considers, coast. So this is like some mixture of words. Now, what is important? Here you asked for 10 topics, but this doesn't mean that you will use all of them. What you need here is the presence of these topics in your documents. So how many documents contain, and it's not that simple as that. You don't have a binary measure that this document contains this topic or not. You have a probability. So you can calculate the expectation of each topic, and topics which you don't find pertinent and have a small expectation, you can simply omit. And you can concentrate on those topics that you consider as being pertinent for your task. Okay, so I've added these because later we will use another method and you will be able to compare. Now, before we stop for the break, I wanted to tell you that besides LSA, there is also an ESA, Explicit Semantic Analysis method. on which I have contributed a bit, and it is explicit because it is based on Wikipedia. So the idea of ESA is that Wikipedia has documents, and these documents have been manufactured in a way that each one represents a given subject. And it's the topic or the title of the Wikipedia page. So using these as a corpus gives me a guarantee that the words contained in these pages are semantically related. So I start with this corpus, with Wikipedia, and I calculate the matrix of correspondence of documents and terms, and the transpose of this will be the matrix of documents with respect to words. So for each word or for each term, I obtain a vector in the dimension of the Wikipedia corpus. And then, of course, I reduce this. I reduce the dimensionality. And by multiplying these vectors, I get semantic similarity between words. So words are semantically close if they appear often in the same Wikipedia pages, which is not unreasonable. It's a measure that works quite well. And instead of Wikipedia, you can take other corpora which are built in a way that pages have some semantic coherence. So this is an extension of LSA, ESA, and then the next thing we will look at is LDA, latent Dirichlet allocation. So this after the break. Now it's 10 minutes to 3. We will start again at 3:05. See you in a moment. Okay, so we saw LSA, latent semantic analysis, and now we switch to a different technology with the same goal, obtaining topics, called latent Dirichlet allocation. So Dirichlet is a probability distribution which is very special because its support is sets of numbers. So we have many random variables, the sum of which the sum of the values of which has always to be 1. So it's like having a probability distribution. So some people say it's the probability distribution of probabilities. Now, Dirichlet distribution has parameters, as many parameters as there are variables, but these parameters are not probability values. It's not between 0 and 1. They can be larger than 1. And here you have examples. The larger your numbers are, the greater your numbers are, more concentrated is probability mass. So here you see a triangle. This triangle is, in fact, you should imagine three-dimensional space. And this is the triangle of values 0, 0, 1, 0, 1, 0, 1, 0, 0. in your three-dimensional space. So it's a triangle which is lying on the on your repère de coordonnées, on your coordinate system. And since every vector of our support set has to be on that triangle, we only display that triangle. And depending on the parameters of your Dirichlet distribution, you have different mass concentrations. Here, for example, you have the third parameter, which is very high, 8, 4, 2. So we are close to this one. And this is 8, this will be 4, and this will be 2, and so on. Now, the idea is that you have two things that are varying. On the one hand, you have topics, and these topics appear in documents, and documents have words. So you have probability coming from topics and going to documents, and then to words included in documents. So it's uniform on words in documents, but it's not uniform for documents. And on the other hand, you have the probability of topics on words. So these are the words contained in topics. So that to calculate the probability of the whole system, you need to take both into account. And here, these boxes display the different probabilistic relations, and the numbers here are the dimensionality. K is the number of topics, M is the number of documents, and N is the number of words. Okay, so how do we calculate this? How do we take both kinds of probabilities, probability of a word belonging to a topic and the probability of a topic belonging to a document? How do we take both simultaneously into account? There is an algorithm which resembles the Kameen's algorithm, in the sense that you start with some assignment of topics to words, and then you improve this and you do many iterations, and on each iteration you improve a bit, and this converges to final assignment of topics to words. Okay, so it's described in 2 slides. So the first thing is to randomly assign topics to words in documents. So a given word can have different topic assignment on each document, in each document. It's really random. And then we prepare matrices of topic presence in documents. So we say this document contains 3 times topic number 1, 2 times topic number 2, and so on. And also tables for topic assignment per word. This word has been assigned 3 times to topic 1, 2 times to topic 2, and so on. As we did this randomly, these tables for the moment have absolutely no meaning. It's just a reflect of our random decisions, reflection on the result of our random decisions. And now we start a loop over all words in all documents. So we start the first word of the first document, then the second word of the first document, and so on. What we do is we remove the assignment of the topic and therefore change our matrices accordingly to this removal. And then we calculate the conditional probability of the topic with respect to the document. So this is the topic that was assigned to the word. This is the document that, sorry, this is the topic that was assigned to the word we removed. This is the document that contained this word. Sorry, we didn't remove the word. We unassigned the topic. We removed the topic assignment to word WJ. The topic was TK, and we are in document DI. Okay, and we calculate these two conditional probabilities as follows. Probability of the topic K, knowing that we are in document I, is the number of words in topic K and document I plus a smoothing parameter divided by the total number of words of document I minus 1 plus the smoothing parameter times K, which is the number of topics. So this is a smoothing version of frequency counting. And here I have the same thing for the probability, conditional probability of the word belonging to the topic. So it's the number of times this topic has been assigned to this word and the whole corpus. And here, the number of times this topic has been assigned to any word in the corpus, with again a hyperparameter, and V is the size of the vocabulary. Okay, now the trick is to multiply these two, because I want to increase both at once, at the same time. So I multiply them and take the K for which the product is maximum. So what is the topic that increases simultaneously and at most as possible the probability of this topic belonging to the document and the probability of the word belonging to the topic? And what I obtain, I assign to this word. So I have de-assigned it, I did these calculations, and I'm assigning it a new topic. And these steps I do for all words in all documents. So this gives me a reassignment of all words. And this is my first iteration. And then I repeat this iteration several times. And this is how I calculate latent Dirichlet allocation. And here's the code. It's almost exactly the same code as in the case of LSA. I only change this. My model is latent Dirichlet allocation and not SVD, singular value decomposition. And here are the results. As you see, we don't have a topic with names except for Brisbane, the name of a town, but not names of people. And here I have both results in the same slide for you to compare. So these are the LSA topics, and these are the LDA topics after 100 iterations. And I can tell you that on my computer, these 100 iterations took a few hours. I think about 2.5 hours. Okay, so how do they compare? Here I don't see Australia so often. I see Australia once, Australian, and that's all. I have some town names, Melbourne, Brisbane. Here I have Sydney, but no Melbourne, no Brisbane. Then this one is not very thematic. You see, you have crash, found, missing, still, state. It doesn't really make sense. Still should maybe be removed. So maybe we should restart this by considering still as a stop word. Same thing with open, or maybe not. Here you have a topic which is more political because you have government, power, union, plan, and farmer. So this looks more like politics. Here you have one which is more around health, but also politics, since you have hospital, health, fear, but also government election win, minister. So you see this combines health and politics, and so on. So we can do the same qualitative analysis in both cases, and we could, as human judges, rate each one of these topics. What we still need is the presence of each topic in documents. How frequent are they? And we could eventually remove some of them if we consider that they are not pertinent enough. When I did my coherence calculations, I surprisingly found a better value. It's better because it's smaller. Remember, coherence is it's bigger. Coherence is the log of probability of the joint divided by the product. So this is smaller than 1 if the words are related, and is close to 1 where they are independent. So we would like them to be related. So we would like this to be smaller than 1. Okay, so this needs some thinking. Okay, but bigger values give a better coherence. And here, surprisingly, we have a greater value for LSA than for LDA. But unsurprisingly, we have a smaller value because it's negative for 1 iteration, and we get a better result for 10 iterations and a better result for 100 iterations. but the difference is very small. As you see, here we still have a difference of 1 unit. Here we have a difference at the second decimal digit. So waiting for 2.5 hours finally didn't change many things. For 10 iterations, it was rather quick. There is also a method for topic extraction based on neural networks. It's called LDA to VEC. So it's a latent directly analysis in a neural network and deep learning context. And instead of explaining it in detail, I'm just showing you some slides from the presentation of this system, comparing embeddings, topic extraction, and LDA to VEC. Because LDA to VEC is, in some sense, a merge of embeddings and topic modeling. When you do an embedding, especially when you do the second kind, skipgrams, then from one word, you obtain the words of context. So you train a word on the word surrounding it. So tac, 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 tac. You see, there is a link between a word and the surrounding words, and this is the link you train your model to recognize and to predict. When you do LDA, you train documents you train words as belonging to these which are aggregations of documents and in fact are what we call topics. So you train a link between a topic and words. Now, LDA to WEC combines the two by creating simultaneously a link between topics and words and words and their surroundings. So by doing this, you have properties of both embeddings and topic allocation, and this can be quite powerful. So it seems that they obtain good results. I have on Moodle, you have links on these systems. We will get there in a moment. So this is all I had to say on topic modeling. And now I switch to the third part of this class, which is about automatic summarization. So what is the problem? Out of a document, create a summary of the document. In French, un résumé. Why do we need a summary? Because we don't have time to read a document, because we want to obtain the essence of the document. We want the computer to understand the essence of the document, and because we want to make it shorter, simpler maybe, and so on. So there are many possible applications. Now this is an old problem in artificial intelligence. It started in the 60s already. And I will start with a chronological approach of the different methods used for automatic summarization. The first method used was by comprehension, by understanding. So the idea was to represent the text in some way So for example, using first order logic or something like that, then reduce this representation and generate a document out of the reduced representation. So if you want to link this with what we have done this morning, it's like saying I have my ontology with lions and giraffes. I have a text about lions and giraffes. This text gives me a set of RDF triples of concepts and relations all present in the ontology and individuals I define. And then this graph, I reduce it. So I take only the main part of it. Now, what will be this main part? Here, for example, are some rules allowing reduction. The first rule is elimination. Peter saw a blue ball can be replaced by Peter saw a ball. So we consider that the color of the ball is not important, as some of you suggested in the answer about simplification. So in fact, logically, Peter saw a blue ball is decomposed in Peter saw a ball, period. The ball was blue. Giving these two sentences, I don't lose any information. And then I can say that the second sentence, so this triple, RDF triple ball is blue, or ball has color blue, is unimportant. So I remove an RDF triple and I keep only Peter saw a ball. This is in one direction, elimination. There is another direction, which is generalization. Peter saw a hawk. A hawk is a kind of bird. So I can replace this by Peter saw a bird. So I'm using a hyperonym. And this also is a kind of simplification for people who don't know all kinds of birds. This is simpler to understand. So if I'm just learning this language, I know the word for bird, but not for hawk, then this has more chances to be understood. Another kind of generalization is Peter saw a hawk, Peter saw a vulture. What is the common hyperonym of hawk and vulture? They are both birds. So I replace this by Peter saw birds in the plural. And finally, a third possibility, condensation. I'm taking a whole process, digging foundation, building walls, laying the roof, and I replace this by the name of the process, which is building a house. Okay, now this promises to be quite efficient because these macro rules can be learned, they can be parameterized and so on. And so depending on the domain, depending on the task, we may use some or not, some rules or others. The problem is that it's difficult to obtain this semantic representation. We will accumulate ambiguity, and this ambiguity will conflict with our reduction rules. And maybe we will understand something different than what is meant, and by removing part of it, we will get something completely different. Now, when people realized this, they invented a new approach, which is by extraction. So extraction means simply omitting sentences, simply extracting important sentences and omitting all the rest. This has the advantage that there is no change of any linguistic material. We are not rewriting any sentence. We are just selecting some sentences. And the other advantage that we can choose the best sentences, and this is something that can be parameterized, learned, and so on. And most commercial summarization programs used in the past this method of extraction. The other advantage is that your sentences have a given order in the text. So here, if you keep this order, then you have a guarantee that you will not change the rhetorical structure of your document, or you have less chances of changing. Now, how do we find the most important sentences? So one idea is to use TF-IDF. So which words are the most characteristic of each paragraph, for example? So we consider each paragraph as a document, find the most characteristic words, and take the sentences containing them. Now, this has some pertinence since it will contain unique words, it will contain words that are different in each paragraph. But are these sentences really the most important ones? In French, this has even more chances of going wrong because in the French language, contrarily to English, there is an unwritten rule saying that you should not use twice the same noun or the same verb. So French is again repetition. And you are encouraged to use synonyms. If you use synonyms and these synonyms, each one has its own TF-IDF, then you will get many unique words, many words characterizing sentences. And then, of course, you need to lemmatize them, you need to resolve anaphoras and so on. And this means that it's not anymore extraction, it's a bit more than just extraction. Programs based on TF-IDF, sorry, it's TF-IDF, not TD. Programs based on TF-IDF didn't provide good results. The second idea is to use prototypical sentences. Now, this may sound very restrictive, but in a given domain, there are some sentences that are abundant and appear almost always. So in scientific papers, you always have a sentence saying, in this article, we will do this. And in the conclusion, you will always have a sentence saying, in this article, we have done this and that. Once you know the prototypical sentences of a given domain, it makes sense to extract only these. And then you can give them scores and so on. A third idea is by taking smaller parts than entire sentences. And we call them lexical chains. So lexical chains are like n-grams. They are chains of words. For example, we can take only nouns and look at their relations in some resource. So calculate in some sense semantic similarity measure among them. And once you have calculated this semantic similarity, you give these word chains a score. So for each sentence, you will have several scores for the several lexical chains. You can aggregate these scores inside sentences and also crossing sentences, and see where you have a concentration of similarity. And use these and take these sentences and extract them. This also makes sense because it means that you have found sentences which are very coherent and have big chances of being significant sentences. Another idea is to say, I'm not looking inside the sentences, I'm looking at what's happening between sentences. So finding rhetorical relations between sentences. And well, I'm calling this a fifth idea, but in fact, it's the same idea. As we have seen in the thread on linguistics, there has been work on discourse markers and on rhetorical relations between sentences. So these rhetorical relations can be marked or unmarked. You may have explicit or implicit discourse markers. And these rhetorical relations give you the essence of the text. So you start with a sentence, the next one will be an elaboration of the first, the third one will be a justification, and so on. When you do this, you get binary relations between sentences. And if you do it in a specific way, you will get a tree, not a graph. You will not have circular rhetorical relations. When you get this tree, and this tree is directed, because you always have a source and a target, then you will find a root in your tree. It's the way we build this rhetorical tree that makes a given sentence being the root of the tree. And once we have done all of these calculations, we can say that this root of the tree is the most important sentence in the paragraph, in the text. And we can visit neighboring nodes using a breadth first parse of our tree, une recherche en largeur d'abord, and this will give us sentences directly connected by rhetorical relations to the root. This will be the first level, and then we can have a second level and a third level. And in this way, we get summaries of our text, and we can choose the size of our summary by taking levels or sentences that are close to the root and then expanding. So from all methods of extraction, this is the one with the most potential, since it's based on relations between sentences. The third approach, which chronologically has been maybe in the 90s, was by learning, machine learning. So we have a problem. It's a classification problem. Find me these sentences that are classified as important so that I can extract them. We can start by giving criteria and then give weights to these criteria. These criteria can be positional, saying the first sentence is always the most important. This is a criterion. And it's the case, for example, in Wikipedia. The first sentence of the first paragraph of a page is always the most important because it's the definition of the subject of the page. But they can also be linguistic, so they can be morphological or rely on frequencies of terms, and they can even be discursive. So we can, again, use rhetorical relations, this time as criteria in a learning algorithm. So we accumulate these criteria and we do our learning on a training corpus and then we test. So this means that we have manually summarized some documents and we create an engine that will be trained on these and produce summaries out of new documents. So this has been achieved. There has been some publications on this, but of course, it also has disadvantages since once again, you don't process the text before learning, before predicting. So you may have anaphoras, you may have different phenomena that are not discovered by the engine, and relations between sentence also get lost if our learning instance is the sentence. Now, in the last few years, there have been methods of automatic summarization based on deep learning. And I will show you one of these methods. We will consider automatic summarization as a sec-to-sec problem. Sec-to-sec means from sequence to sequence. So this means we are not in the back of word paradigms where you have words without order. Now we have sequences. These sequences can, in general, be words, but they can also be DNA, proteins. They can be many things that arrive in a given order. So it's very general situation going from a sequence to a sequence. And one way of dealing with this is by using long short-term memory, LSTM networks. We will see how they are built, and using two of them communicating, an encoder and a decoder. So when I say two, they are actually layers, but from a structural point of view, it's like having a first network with a single output that arrives to the second network. So we will call these encoder and decoder. So X's are words of my input, and the Y's are words of my output. And what happens is that I process my input, and except for the first, for every other word, I use both the word and information from the previous state. So not the previous word, but the state of the engine for the previous word. So this is a calculation that happens in a given order. We call this the time steps. This has nothing to do with your errors, with your iterations, propagation, and so on. It's inside a single propagation. You have time steps, and at each time step, you use the information arriving from the previous layer, and in the same layer, the state of the previous time step, which means that the order of words is taken into account, even though when I arrive at the fourth word, the influence of the first one has practically vanished. So I'm taking mostly the previous word into account, maybe a bit also the one before, but on the long range, I have no influence anymore. So this is my encoding part, and this information is transmitted to the decoder. The decoder will use here a fixed token called the start token, the start of the sentence, and information arriving from that level. With this, it will produce an output, and this output will be used at the next time step in order to produce the output for the second word, and so on. Let us see that in detail. So we have two pieces of information that are transmitted from one time step to the other. It's what we call the hidden state and the cell state. And we input the first word, we get this hidden state and a cell state, and we transmit hidden and cell state to the next time step where information from the second word arrives, and so on. When we end our sentence, we take the states hidden and cell of the encoder and supply it to the decoder. The decoder will take the start token and produce an output Y1, which will be used as input. So this is a prediction of the first word of the output, and this will be used together with these states to predict the second word. So in fact, in our output, we produce words, we predict words as being the most probable continuation of the previous word until we arrive at the end of the sentence. Now, this is learning. So here, Y1, Y2, etc. are getting close to the result we want to obtain, which means that we will have texts, summaries, and we will train our network to obtain summaries that are close to the ones we have. When we will do prediction, then this will be the same, but here this first time step will give us probabilities for all words. We will take the word with the highest probability as a prediction of the first word of the sentence, and we'll use this one for the second step, and so on. As I said, the problem with LSTM, long short-term memory networks, is that you are losing long-range dependencies. To avoid this, we have what we call the attention mechanism. It's not the only way, but it's one very popular way for improving these networks. The attention mechanism is adding a new layer that will take all hidden states of a given sentence, both from the encoder and from the decoder, and will try to combine them. And it will try to learn a way of combining them. So a score calculated out of combinations of states, both in the encoder and the decoder. And one popular way of calculating these is by linear product. So it's not the only one, but it's a practical one. So I have a matrix W, which is completely independent of the matrices we saw in the previous part of the lecture. This one is about combining hidden states. And while you are training your network, you can give values to this matrix, and it will improve long-range dependencies, because the first hidden state of the encoder may be related and heavily weighted together with the last state of the decoder. So imagine you are translating from a language which puts the verb at the beginning to a language that puts the verb at the end. Then these verbs are connected, since one is the translation of the other. And this attention mechanism will help you focus on this connection between these parts of your sentences. And here's an example taken from the Wikipedia page on the attention mechanism. If I take je t'aime and I love you, the attention mechanism will give a high weight between I and je, high weight between aime and love, and a high weight, a bit smaller weight between te and you, and very low weights in the other cases. And this improves processing. In our case, it will be summarization a lot, because it reveals hidden connections between parts of sentences. And from a site for which I have placed the link on Moodle, you can see some examples. So this is a case study on Amazon Fine Food Reviews. It's a very large corpus with millions of reviews. And these reviews always have a title. We can consider the title as being the summary of the review. So they are quite practical. Well, it's a bit telegraphic summary. It's not really a summary in the formal sense, but it's still the essence of the text. So you have the review, which has been processed. So it has become a bag of words, stop words have been removed, and so on. This is the original summary, so it's actually the title of the Fine Food Review. And this is what has been predicted by the network in this project. And there you have the code, so you can test it by yourself. And it's quite interesting because you see sometimes the original summary is longer than the predicted one. Sometimes the predicted is longer. And sometimes the predicted summary is even more informative than the original one. So the original one is delicious, but you don't know what is meant. And it mentions chocolate, but also cream, Malomars, and here, best chocolate I've ever tasted. So this is really only about chocolate. And here you see taste terrible. So really negative review, not that great, is a bit less negative, but still negative. In some cases, the result is not very convincing. So here it was not bad, has some ups and downs, and the predicted summary is not as good as it is. So we don't really get the meaning of this as it. So what is it? But still, it's a nice prediction, and it's a very simple neural network. So this is my last slide. Today we saw embeddings, topic modeling, and automatic summarization. And now for the time that remains, or for your curiosity, I have gathered some links that are on Moodle. So where's my Moodle page? Just a moment. Maybe I accidentally closed it. Here we are. So this is the Moodle page of our class. And here are the next questions I want you to answer. Here are the next questions I want you to answer. I have to display them. Voila. And here are the slides we saw today. And here are some useful links. So here you have a chapter of a book on embeddings, which is very interesting. Here you have the code and explanations. And a Jupyter notebook on LDA, a tutorial on coherence, again with the Python code, different kinds of coherence and how we calculate them. Chiara's tutorial on sequence to sequence in general, written by Francois Chollet in person. So this is about sequence to sequence in general, and allows you to understand how it works. This one is on LDA to VEC, So topic modeling uses using neural networks. So here you can compare the results, you obtain the results and compare them with LSA and LDA. And finally, a page on text summarization. So this is a very interesting page. And this is where I took the examples. So it gives you a link for the corpus, Amazon corpus, and code for the attention layer, which is not by default included into Keras. So you have to import it, and then you can use it as all other layers. And here are the results I just shown you. So you're free to choose the page you like the most. All of them are useful and well done. And you can also keep them aside for later. If one day you have a problem in this area, then you can always come back and see how it was solved. So now I will close this last lecture.